Hello, welcome to our GraalVM webinar series. And this time we're joined by Randy Stafford from the Coherence team. And sorry, Randy. Randy, can you introduce yourself a little bit?
Sure. Hello, my name is Randy Stafford. I am the product manager for Oracle Coherence. I spent 5 or 7 years on the Coherence product development team before becoming product manager, and I'm happy to have you here today. Thank you.
Well, thanks for coming, Randy. I mean, we were old friends. We've met each other, a long time ago, so I don't know why I'm calling you Andy. So Randy's going to talk about how GraalVM has been integrated into Coherence to add new functionality. And I guess, Randy, you'll introduce Coherence, what it is, and I'll pass it over to you.
All right. Thank you, Sean, and hello, everybody. Again, I'm Randy Stafford, Coherence Product Manager, and I'll be speaking today about how we achieve polyglot programming with GraalVM Enterprise Edition in Oracle Coherence. So I do need to give the safe harbor statement because there's a bit of future-looking information at the end of the presentation, and also point out that the GraalVM native image is in early adopter status, so it has an additional caveat here. So our topics today, I'll talk a little bit about Coherence, what it is, and grid-side programming in Coherence. I'll give a little overview of the GraalVM Enterprise Polyglot API that we use, and then I'll show how we use it on the grid side in Coherence 14.1.1. And the final section is a bit about the future of polyglot programming in Coherence with GraalVM Enterprise. So to dive in, Coherence is an in-memory data grid. It came to market in 2002. Oracle acquired it in 2007, and it has been important for scaling mission-critical systems all along. In fact, the web conference technology that we're using today from ON24 actually incorporates Coherence in its architecture. ON24 has been a Coherence user for at least a decade now. So Coherence is a key value store that provides fast access to data with optional disk persistence. We do automatic sharding of the data in a fault-tolerant way so that application code doesn't have to know where a given key value pair lives in a cluster. We have Polyglot and REST client interfaces. By that I mean we have native Java, native C++, and native .NET interfaces, plus a REST interface. We have some data management features like querying and transactions and eventing that are relevant to the grid side polyglot code I'll be discussing. We have an in-place processing feature that allows you to run code where the data lives, analogous to stored procedures. You'll see an example of that in JavaScript on the grid side. We have a feature for refreshing caches from the database called Hot Cache, uses Golden Gate. We have multi-site data federation capability, and in our newest release, 14.1.1, we introduced a messaging implementation on top of Coherence. And from an operational perspective, we support Docker and Kubernetes and distributed tracing through Coherence. We tend to sit between services and enterprise data sources and cache data that's used by services. So that's a little introduction to Coherence. Now let me talk about briefly about use cases for Coherence. Users use it to improve the performance and scalability and reliability of their systems. Probably the most common use case is just fast data access and back-end offload at very high scale. We're capable of managing single-digit terabytes of data in a Coherence cluster, and some of our largest customers are accessing the cache at about 1 million TPS. We are also used for grid computing, for example, risk analytics applications in financial services industry where the logic runs in the grid, co-located with the data for fast algorithm execution. And we are also used for event-driven architecture where the data grid caches data that's coming in from sensors, and events are fired based on incoming data to interested parties. So those are some of our use cases. And let me talk a little bit about our query functionality that I mentioned on the first slide. So we are able to, if you want to select data by something other than the key, we support that with a query subsystem, and we distribute the queries across the cluster. So in this diagram, the cloud or popcorn-shaped icons represent JVMs. They represent Coherence cluster members, each of which owns a number of partitions of a cache or one or more caches. And we distribute a query. In this example, we're trying to select the set of cars from the cars cache that are the color red. So we distribute that over all the storage-enabled cluster members, and each one answers with its subset of the red cars, and the result gets assembled back to the caller. So this parallelization of query execution results in fast response time. We can handle the case where a storage member dies during the middle of query execution. We resume the query on the new primary owner of that partition when the partition transfer happens. And we do have indexing in our query subsystem for efficiencies to avoid the equivalent of a full table scan to answer a query. And the reason I wanted to show this particular feature is because we can do it in polyglot languages now, whereas prior it was done in Java primarily, or for using some of our out-of-the-box filters, it could be invoked from any of the other native client languages. So we'll see an example of a filter written in JavaScript a little bit later. Similarly, we have Mapreduce style aggregation. So in this example, we are counting the number of cars in the cars cache that are red. So previous example was basically select star. This is select count star. So again, we send the aggregator to all the cache servers owning partitions of the cars cache, and each cache server answers the count of red cars that it owns, and the reduce phase, the sum of all those individual counts happens next and is returned to the caller. So that's an example of aggregation, and later we'll see an aggregator written in JavaScript running in these JVMs on GraalVM Enterprise. Finally, we have in-place processing that is very helpful for concurrent updates. Instead of a lock, get, modify, put, unlock sequence, we can just invoke what we call an entry processor or a Java Lambda, and it is executed in the cache server that owns the key value pair you're invoking it on, the entry you're invoking it on. And during the entry processor execution, that particular client or thread has exclusive access to the partition containing that key value, so it solves the concurrency problem. And we don't return control to the client until after the changes are backed up to the backup partition owner. We guarantee idempotency of this, and we also have a feature called partition local transactions, whereby one client invocation can modify multiple key value pairs in the same partition as a transaction. So it's a lighter weight, faster executing transaction model than, say, XA distributed transactions. And we'll see an example of an entry processor written in JavaScript a little bit later. So that's a little introduction to Coherence and what the product is, what the use cases are, some of the grid side features, querying, aggregation, and in-place processing that can be written in polyglot languages with GraalVM Enterprise now in our 14.1.1 release, which, by the way, just came out at the end of March. So let's talk about the GraalVM Enterprise Polyglot API real quick. GraalVM Enterprise supports multiple languages running on JVM. You can see some of the languages here, obviously Java, JavaScript, Python, Kotlin, LLVM languages, R, Ruby, etc. All of these languages can run on the GraalVM. So there is a feature of GraalVM Enterprise called the Polyglot Api, and here's a little just bulleted overview of it. The Polyglot API allows you to embed and run code from what they call guest languages in JVM-based host applications. And the GraalVM supports languages implemented with this language implementation framework. We have examples of the Polyglot API in JavaScript, R, Ruby, and Python. You'll see this on upcoming slides. You can define guest language functions as values in Java. I believe this is the Polyglot API class, capital V value. And you can access guest languages directly from Java and vice versa. You can access Java from guest languages on the GraalVM, and that includes type lookup from guest languages of Java types. You can restrict access of guest languages to Java platform or application functionality so that a guest language script you're running can't call system.exit, for example, and terminate the JVM that's executing. And you can instrument the guest language execution with an execution listener that's provided by the GraalVM Polyglot API. And there's a couple of other features here that I didn't list, but it's a pretty interesting, pretty powerful framework for multi-language execution on a JVM. So here's an example of the Polyglot API. This is Java code that is evaluating a JavaScript function. It's a simple function that just increments a number and returns it. So here we get a context object. We tell it to evaluate some JavaScript. The result is an instance of value representing that function. It responds to can execute. It responds to execute, and we can assert that passing 41 and incrementing it by 1 returns 42. So a simple example of a JavaScript function as a value in Java that can be executed. Here's another example of basically direct JavaScript from Java, not a function. In this case, it's a JSON document that we evaluate via a context and get a result. We can assert that the result has members. It's a JSON document with multiple members. We can access the members by key, essentially, and we can assert that one of them has array elements and so on. So this is an example of Java code through this value class interrogating a JSON structure. Here's another example of the Polyglot API. This is JavaScript code accessing a Java application class. So we define this class called myClass. It has some fields. Interestingly, one of the fields is a callable. And so here's some JavaScript code that is accessing an instance of this myClass that's passed into its context. So the JavaScript code can ask for these fields, the ID, the text, the array, and the JavaScript code can even invoke that callable and get back the values of those fields. So that's application Java class being accessed from JavaScript code on the GraalVM via Polyglot API. Final example is JavaScript code accessing a JDK class in the Graal Polyglot API. So here we have some JavaScript code that's getting an instance of the Java type Java math big decimal and is raising that big decimal is raising 10 to the power of 20 and then converting it back to a host object and asserting that it equals 10 to the power 20. So this is JavaScript code accessing a JDK class in Java. So those are just a few examples of what you can do with the GraalVM Enterprise Polyglot API. And now let me talk about how we've used that in Coherence to implement grid-side code in JavaScript in these examples. So as I mentioned, Coherence 14.1.1 was released in late March and is certified with Oracle GraalVM 19.3.x, GraalVM Enterprise. And we also certified Coherence 12.2.1.4 with GraalVM Enterprise 19.3. So you can run Coherence 12.2.1.4 on GraalVM, but the Polyglot API usage came with 14.1.1. What we did in Coherence 14.1.1 with the Polyglot API was we allow you to write grid-side code in non-Java languages, and initially JavaScript with more coming. We certified running Coherence on GraalVM out of the box, including our Docker images can run on GraalVM or contain GraalVM. And this also allows you to embed Coherence in non-Java applications. For example, you can connect to or host Coherence in Node.js processes. And in the pretty near future, we'll have a demonstration that shows exactly that feature. So interesting new flexibility. So what we did for grid-side code in JavaScript, we allow you to write filters that are used in distributed queries. We allow you to write aggregators, like we saw in the count cars example, and we allow you to write entry processors in JavaScript. And the JavaScript code that you write operates on cached Java objects stored in Coherence cache servers. Just a bit of technical detail on how we accomplish this. We use some components from Node.js to set up these grid-side JavaScript projects, and we put the JavaScript artifacts into a well-known location, which is put on the cache server's class path. And then when we start up a Coherence cache server, we evaluate all the JavaScript files in that well-known location and cache the JavaScript classes. So that's a bit of mechanics. I'll show you some of the ways this is used now. So here's a JavaScript filter class that basically returns true if a car is red. Just JavaScript's syntax for string equality from the color attribute of a car. And then here is an example of Java code invoking that JavaScript filter against a cars cache, finding all of the red cars and printing each one. So in Coherence, we have a class called named cache in Java, which has a getAll method, and you pass to getAll a filter. And in this case, we're asking for a JavaScript filter name registered as is red, and we're running that filter on the cars cache. So that's an example of a distributed query using a JavaScript filter. Here is a JavaScript aggregator, and as you saw earlier, our aggregation functionality is essentially Mapreduce. It's two-phase. So the contract of an aggregator, in the first phase, this accumulate method is called with each cache entry in a given cache server or partition that's targeted. And in the reduce phase, this combine method is called with the results from all different cache servers, and finally the finalized result is called. So this is a JavaScript implementation of our aggregator contract. Basically, the aggregator is trying to find the car with the maximum mileage. So we initialize mileage to 0. As we go through each partition's entries, we pick the one that exceeds our current max and so on. And then when we're reducing, we pick the one that has the max across all the different partitions. Here is Java code invoking the max mileage aggregator written in JavaScript. So again, our named cache type has a method called aggregate, and what you pass to aggregate is an entry aggregator. So we are targeting the entry aggregator against all the red cars, and we're asking for the aggregator named max mileage that's written in JavaScript. So the result of this will be which red car in our cache has the highest mileage. So showing a JavaScript entry aggregator implementation being invoked from Java. Finally, I mentioned entry processors that do the in-place processing in a critical region. So here is a JavaScript entry processor that increments the mileage on a car. So we have JavaScript class called mileage incrementer. We can take a constructor argument, which is the amount by which to increment each car's mileage. And entry processors have a process method, which is passed a key value pair, a map entry. And we get the value of the key value pair, which is a car, and we basically add to its current mileage the increment that we were constructed with, rebind the value into the key value pair, and return the mileage as incremented. Here is some Java code which invokes that entry processor. In this case, we're invoking it on every car in the cache of cars. We're asking for the entry processor written in JavaScript named mileage incrementer, and we're going to increment every car's mileage by 1,000 that's in the cache. So those are examples of filters, aggregators, and entry processors written in JavaScript invoked from Java. And finally, my last topic here is what we're doing in the future with polyglot programming and Coherence enabled by GraalVM Enterprise. We want to open access to Coherence to basically every language we can. Started out in Java, added .NET somewhere along the line, added C++ after .NET, then added a REST API. Now, especially with GraalVM, we can support newly popular languages like JavaScript, Python, some of the mobile platforms like Android and Swift, Go, etc. We want programs written in any language to be able to access Coherence caches and services without necessarily caring and having an equal API for all those languages. So in 2020, we are implementing native language clients for other languages. We're implementing them on gRPC, which is an alternative to Coherence's extend protocol, which allows non-cluster member processes to connect to a Coherence cluster and access cache contents. gRPC is desirable because it's a modern open source framework for a remote procedure call. It supports HTTP proxies and transport layer security. It supports asynchronous client-server communications, allowing interaction styles like reactive, for example. And we have an asynchronous implementation on the grid side of our gRPC feature. So with gRPC in place, we will begin rolling out native libraries for Coherence access from these languages I mentioned. And if you're using one of these new native language libraries, you can write asynchronous or reactive clients. And in calendar year 2020, we are introducing JavaScript and Python. So this is all happening on the client side of Coherence. And what we want to do on the server side with GraalVM Enterprise is support more grid-side languages. All the examples I just showed you were in JavaScript, but we would like to be able to run the same languages on the grid side that we have on the client side. And furthermore, we would like to allow the grid side code in the same language as the client side code to be invoked without the intervening Java. In all my examples, you saw where I had a JavaScript filter or aggregator or entry processor, and then I had a piece of Java code to invoke that. We want to be able to do that seamlessly with knowledge of the client language to basically automatically select the right grid side code to run based on the client language. We do want to quantify the performance improvement that we're seeing from GraalVM Enterprise. The Polyglot API is just one feature. One of the main thrusts of GraalVM is basically faster execution, faster startup, more efficient memory usage. We've observed these benefits anecdotally, but we've yet to quantify them because our focus was on Polyglot. And finally, for the client side, we want to explore native image compilation, which is yet another GraalVM enterprise feature, basically making an executable, not interpreted version of a program. So this is where we're going with Coherence GraalVM integration going forward. And what we have today is the server-side JavaScript that I showed you. So that concludes the presentation.